In this next video, I will show you when to use the normal curve as an approximation to the binomial distribution. So I'm sure you're thinking, why? Why would I care? Why do I want to know? Why would I use the normal distribution as an approximation to the binomial? You just taught me how to use the binomial. And I would say that's a good question. And I honestly don't have the best answer for you. Perhaps in the past we didn't have such great technology as we do today, and therefore we wanted to have just maybe a couple of tables instead of many tables to use. So instead of using binomial distribution and normal distribution, we go, oh, well, you know, the normal curve is really cool because actually when certain circumstances, binomial it looks a lot like the normal curve, and the normal curve can represent binomial. So I'll show you when that is. We're just going to do an example here.
And if I go ahead and I am going to say, oh, I don't know, we have a, for example, 0.06 probability of being, I don't know, what was it, O positive or something like that. If you randomly choose 5 people, n equals 5, there are 5 trials, and you have a 0.06 probability of, you know, having a certain blood type, well, the probability that you have 0 out of those 5 have a certain blood type, well, that's a 73%. The probability you have 1 out of those 5 is a 23% approximately. 2 out of the 5, 3%. 3 out of 5, that's more than half, you have a less than 1%, and 4 out of the 5, practically 0%. Of course, that's because it would be a very small probability to get 4 out of 5 people have a certain characteristic, certain blood type, when there's only a 0.06 probability for the entire population. Well, let's bring it up a little bit. Let's bring it up a little bit. Let's go ahead and bring it to, oh, I don't know, 20 people. With 20 people, well, you have a little bit more chance of having 4 out of the 20. However, there's no way you'll have 14 out of the 20. This is scientific notation. So that's 2.095 times 10 to the negative 13th. That's 12 zeros and then a 2. So that's very, very improbable. Of course, the probability that you have, you know, less than or equal to 14 is almost 1. You have an almost 100% probability that less than or equal to 14 people will have this characteristic. But you can definitely see that this is right skewed. I mean, we had 5 people, it was right skewed. 20 people, it was right skewed. Let's try 50 people, still right skewed. Let's try 100 people. Hey, look what's happening. It is becoming more and more normal. So if I have 200 people, this really looks a little bit more like a normal curve. If I have 300 people, even more normal. So now if I have 500 people, there's definitely much more normal, the curve looks much more normal, normally distributed. It's symmetric, it has unimodal, and it has these 2 tails, etc. So it looks normal. What's happening is as we increase n, the binomial probability curve looks more and more normal. Well, when you have a probability of 50%, well, it is already symmetric. Even with 10 people, it's symmetric. Of course, if we have 20, it looks more and more normal still. So you get to normal, or you get to a normal, you know, approximation of a normal curve a lot faster if the probability is not 0.06, but if the probability is 0.50. So basically the idea is if P and N are big enough, then you will have an approximately normal curve. Another way to say this is like, well, don't just tell me if it's big enough, give me some rule of thumb. Here's the rule of thumb. If NP is greater than or equal to 10 and NQ is greater than or equal to 10, then you can use the normal curve, normal distribution, as an approximation to the binomial distribution. This is another way to say this is that if your expected number of successes, remember this is just your mean, if your expected number of successes is greater than or equal to 10 and your expected number of failures is greater than or equal to 10, then you can approximate binomial using normal. And when you do that, well, now you can use the normal calculator, and the normal calculator requires that you have some mean and standard deviation. In this case, our mean is our expected value, or NP, and our standard deviation is the square root of NPQ. Okay, so let's compare our binomial to our normal approximation here. So for example, if we have n equals 200, p equals 0.06, let me make sure that our NP and NQ are greater than or equal to 10. Let's see, NP is 200 times 0.06. That's 12. That's greater than or equal to 10. We're good there. 200 times 0.94, definitely greater than or equal to 10, so we're good there. All right, so we can use the normal approximation. And so let me go ahead and put these side by side. If I have a mean, for this we have NP is equal to 200 times 0.06, which is 12. Our mean is 12. Our standard deviation is 200 times 0.06 times 0.94. Which is 3.36. If I want to find the probability of less than or equal to 5, you can see that it's slightly different. For binomial calculator, we have the probability of less than or equal to 5 out of 100 people is 0.0177. And the probability of less than or equal to 5 using the normal distribution as an approximation is 0.0186. And therefore, they both round to the nearest hundredth in the same place, but using the approximation, it's not exact, it's an approximation, but we can still use it.